And welcome to episode 9 of the electronic experimenters kit, the common emitter amplifier. Before we start the main video, I'd like to say a word about this video's sponsor, PCBWay. As you can see, at the moment they're having a 9th anniversary promotion, offering free coupons, up to 50% off PCBs and assembly orders, unboxing blind boxes, a chance to win free modules, and sponsorship for your non-profit project. So, there's only 7 days left, so get over there quick and get your next project going. And where do we start? Here we have a white sheet of paper. What's the first thing we need for a common emitter amplifier? We need a transistor. Let's start with a transistor. And what do we need then? We need some resistors. So let's add some resistors. So we'll start off, we want one there, we want one there, one up there, and one down there. So we have some bias resistors, we have a collector resistor, and we have a emitter resistor. So now we need to join them together. We want to have a supply on it, so and we want like a 0 volts, so we want a ground. We'll have a ground and we'll plug it down here. Alright, so fits on the screen. So there we have it. So we'll just make it look a little bit prettier. So there we have it. What's next? So where are we going to start? Well, I like to start down here because it helps me set this point. So we'll start with R4, the emitter resistor. As it's with this, I can set the emitter quiescent current and hence the collector current. So I can decide what emitter current I want and what voltage I want across the emitter resistor to be set to in this example. I've decided on 2 milliamps and about 1 volt to make the maths easy. So 1 volt divided by 2 milliamps equals 500 ohms, or 470 as preferred value if you're going to use something like the E24 range, i.e. 5%. We make that 470 ohms. Now we look at R3, which is the collector load. We want about half a supply voltage dropped across this to set the collector at about mid-rail, which is about 4.5 volts, there, give or take. So what we're going to do with this, and we're going to say that R3 is effectively half of 9 volts, which is 4.5 volts, divided by the 2 milliamps that we want flowing down here, and that gives us a value of about 2K2. Well, actually it was 2.250, but 2K2 is a preferred value, so there we go, we'll have that. But no, these are only approximates, but should get us in the right ballpark. We could do better if we had a transistor curve tracer and we could characterize the transistor we're going to use. But at the moment we haven't even looked at the data sheet for this transistor. So we're just ballparking around it. Right, so next step, set up the biasing. Now I need to set the base 0.6 or so volts above the emitter voltage. It will take care of itself. It will adjust the current flowing through R4 to give the right base voltage. And so, it's not going to be exactly what I set it to. It's going to be around there somewhere. I want to set the current coming down here to be about 10 times what's going in here, so that the current changes in here don't really affect this voltage. We could look at if this has got a HFE of, say, for an example, 100, then we would have 2 milliamps flowing down here and 100th of it flowing in here, so about 20 microamps. So this set is 10 times bigger, so that we're going to have 200 microamps flowing down here, or possibly like 180 through this bit and 20 down there, but we'll just say it's going to be 200 coming down here. What do we know? R2 has 200 microamps flowing through it. We were setting that for 1 volt, so that's 1.6. We have 1.6 volts across it, which gives us about 8K. But the preferred value is 8K2. So we'll stick 8K2 in there. Right, that leaves us with R1. Therefore R1 is the 9 volts minus the 1.6 divided by the 200 microamps, which works out as 7.5 volts across here ish, and 200 milliamp microamps flowing through it, which gives us about 37.5k, but a preferred value 39k. There we have it, our circuit. So we can, and later on we can measure these voltages and see how we're doing. So the next thing is, let's build it. Just a quick note, let's put in the voltages that we expect to see. So our design was aiming for 1 volt on the emitter down here in brackets. We were aiming for 1.6 volts on the base, and we were aiming for 4.5 volts on the collector, and 2 milliamp flowing down here. So that's just a reminder. So start with a blank pegboard. We'll pop up the circuit so we see what we're doing. And what do we need? We need somewhere for our emitter resistor to go, which is 470. We need the transistor to have somewhere to live. So transistor, we need the collector resistor. We need a junction point off the base for the 2 biasing resistors. And then we need the bottom biasing resistor, which is 8k2. The top resistor, which is 39k. We need somewhere to bring the power in, the 9 volts and the 0 volts. We need the supply, to the top 2 pins. And we need 0 volts to the bottom. We'll bring the multimeter in so we can check the voltages and see if they're close to what we calculated. Supply on, and we'll check what we got on the supply. 9 volts on the supply. We have 8.53 volts on the emitter, and 1.49 volts on the base, and we have 5.02 on the collector. So if you add them to that's what we were expecting. And what did we get? We got 5.02 measured there, we got 853 on the emitter, and we got 1.49 on the base. So less than 1 volt, which means we are pulling less than 2 milliamps down here, but close enough. You know, we aimed for 4.5, we got 5. You know, we're 0.1 out of here, a little bit more here. So we were aiming for 4.5, we got 5. We aimed for 1, we got 0.83. We aimed for 1.6, we got 1.49. All roughly in the right ballpark without taking any of the real characteristics of the transistor into account. So next we should look at the gain. And to do that we need to add some parts. And the components we need to add is a capacitor, as we need to decouple the output. We'll say that it's 10 mic, and we need one on the input. There we have it. Bring it out of the way, and Miraculously, there's the capacitors. The circuit was updated. So now let's calculate the gain. And for that, we'll bring this screen back over a bit so we can look at it. And we'll talk about the gain. So, gain, that equals minus RC over RE, RC over RE, but RE is plus R-E, which is the intrinsic resistance of the emitter, which at about 17 degrees C gets calculated out to be about 25 ohms with 1 milliamp of current flowing. Or we say we've got 2 milliamps of current flowing, so we're half that, so the intrinsic resistor in the emitter is 12.5 ohms. We add that to our 470 and the answer comes out as minus 5.6. The gain is negative. As a single transistor amplifier is negative. It's an inverter, i.e. it's an inversion of the input signal. Didn't say that very well, but that's what it does. Right, so let's push that out of the way and put it up there. Alright, to start looking at the gain, we'll bring in our oscillator. And we'll be feeding that about 10 millivolts. Put channel 1 on the input, if it will hold on to. We will put channel 2 on the output, and we'll bring in the scope, power on. And you'll notice that the scope, both channels are 50 millivolts per division, and the input is in yellow, which is smaller than the output in blue, and it looks about 4 times. So let's measure it. Let's bring in the meter again, bring that in that we can see it. Put it on AC, hopefully this will measure this low. So there's our input, approximately 10 millivolts AC, about 1 kilohertz, and we'll put it on the output. 46. So we calculated the gain to be 4.56 and it measures out at 4.6. So that is a successful design, and that is the common emitter amplifier